Okay, hello. We are in the middle of a unit on limits, and we have been learning about the formal definition of a limit, that is the epsilon delta definition. And in class, we mentioned that there were some limit laws. We proved a couple of them, and then I mentioned a couple that we didn't prove in class. And okay, for my own students who are watching this is an optional video. For anyone else who stumbles upon this, this is the kind of thing that you might do in an upper level calculus course, an analysis course, or if you're in a very ambitious high school calculus class or introductory calculus class in college, then this is the kind of thing you might prove as well, or you might just be interested. And I'll say that these proofs are often found in introductory calculus textbooks that treat the epsilon delta definition of a limit. And the proofs are often like extremely complicated and kind of annoying. So I'm going to hope, what I'm going to do right now is I'm going to prove these three limit laws. These are sort of three basic limit laws. I'll state the three laws. First, the first one says that if you're taking the limit as x approaches c of some function, which is in fact just a constant, b is just a constant here, times some other function, f, then what you get is simply b times whatever the limit as x approaches c of that function f is. Okay, so built into this limit law is, so this is just a theorem. Built into this limit law is the idea that this limit exists. So assuming this limit exists, which means it's a number, then this limit is just going to be that number times b. Okay, that seems very reasonable, and it just says that you can, pull a constant out of a limit. Okay, well, what else? The second one is basically says that the limit of a sum is the sum of the limits. Once again, if you have some function f and the limit exists as x approaches c, and you have some function g and the limit exists as x approaches c, in other words, they're both numbers, then the limit of the sum of those two functions, you can think of this as its own function, is just the sum of those two limits. And also with the product. Okay, great. I think I mentioned to my class that this appears maybe not at all. This appears in the body of the text, though I think their proof is often very confusing, and I think many textbooks have proofs that are confusing. The proof of this third limit law is in the appendix of our textbook, and it's actually just impossible to follow. It's extremely impenetrable, and I don't think it needs to be. So, okay, we're going to begin with number one. I guess maybe one final comment, which is, once you've proved that in general the limit of a product is the product of the limits, then you don't really need this first law anymore because, b is its own function. So in some ways this first proof is a special case of the third one. Still though, we do it. Okay, let's go. Let's go. So how are we going to do this? Oh, and I suppose I need like b to be not 0 or something like that. Okay, actually let's start with our first limit law. What is the limit law? It says that the limit as x approaches c of b times f of x is b times the limit as x approaches c of f. Alright, and I think just to keep things kind of simple, I will just let b be positive. Let's just do that. So let b be positive. If b is negative, then you have some annoying little steps in the argument, and I don't feel like doing. Therefore, you can get like absolute values involved and stuff like that. But let's not do that. Let's just treat the b as positive case. If b is negative, it's just the same thing. And yeah, okay, well, like I said, this theorem, so this is our first theorem that we're going to prove, assumes that this limit on the right exists. Okay, so let's just suppose that the limit as x approaches c of f of x is just some number, let's call it L. And yeah, great. Well, What makes this kind of fun, I think a little bit, or at least not a total waste of time, there's some sort of learning that happens here, is you get to take a new perspective on epsilon delta proofs if you've only done the most sort of very basic kind of thing with epsilon delta proofs, which is to use the definition to prove that a certain limit exists, then that's a certain kind of a thing. But here, what we're going to do is we're going to use the definition in kind of a different sort of way. That is, by assuming that this limit exists and is L, what I actually already know is the full definition. In other words, okay, if this limit is L, what does that actually mean? That means that for all epsilon greater than 0, there exists a delta greater than 0 such that for all x, and here I think it's maybe more convenient to use the kind of more succinct absolute value version of the definition, but that is that if I am within, if I'm not too far away from C, so if the difference between me and C is less than epsilon, then the difference between my function and L, if that's less than delta, then that is less than epsilon. Okay. So, what am I doing? I'm simply just citing the epsilon delta definition of a limit. So this is something that I already know just by assuming that this is L. Okay, and so what is it that I need to prove? Well, I need to prove that I just need to prove that this limit is BL. Okay, so I need to prove that the limit as x approaches C of the b times f of x function is just BL. Okay, and what does that mean? That means I need to prove I need to prove that for all epsilon greater than 0, there exists a delta greater than 0 such that for all x, and now, what is this for all x? Well, if I am within delta of C, then my function, which in this case is the function bf of x, is the gap between it and the thing I am trying to prove is the limit, BL, is less than epsilon. Alright, so there's already kind of a lot of stuff going on here. I'll put sort of a red box around this because it's one of the assumptions of my theorem that this limit exists, and so I'm just choosing to name it L, and here I'm sort of stating what it means for this limit to be L. The epsilon delta definition of a limit says that this is in fact what I know, this fact right here. And okay, in like purple or something, I will put a box around the thing that I'm trying to prove. All right, and okay, so what's kind of next? Maybe next we should kind of try to work backwards and figure this out. So in my class we call this a discovery phase. So what is the discovery phase? The discovery phase is where you start with the thing that you're trying to prove and kind of work backwards and sort of mess around to kind of figure out the proof in advance. And ultimately, what is it that I need to prove here? Well, I'm going to get challenged with some epsilon. I'm going to respond with some delta. And this is what I need to figure out. I need to figure out, how to respond. And, well, what should be true about that delta? Well, the delta is how close I need to get to C, such that all those x values have the property that when I plug them into the function, and here I'm speaking of the bf of x function, that it's not too far away from BL. BL being the thing that I am claiming to be the limit. So the whole proof is that this is the limit, and so that is the sort of target there. That the outputs of this function are not too far away from BL. Specifically, they're less than epsilon away. Okay, so this is a lot of talking. I haven't really done anything yet. But ultimately, this is what I need to prove, right? That the gap between b and the difference between bf of x and bl, I have to show that that is less than epsilon. Okay, how am I going to do this? Well, there's just kind of a sort of obvious algebra thing to do here, which is to factor out the b. And yeah, if you factor out the b, then you get b, absolute value, f of x minus l, is less than epsilon. And okay, here I'm using the fact that b is positive. I guess it's not too much more work to just do it in general, to be honest. But if you were doing it in general, then you would have a you would keep the absolute values around the b. So that's basically the only difference. Okay, so well, that's kind of interesting. What else can I do? Well, if I divide both sides of this by b, then I get that the difference between f of x and l is less than epsilon over b. And now I sort of pause to kind of think for a minute about what this really means. I sort of remember this is the discovery phase. This is not the actual proof yet. This is me just kind of doing some scratch work and kind of messing around. This is my target. This first line right here. And so in order for this to be true, remember, I'm trying to discover the delta that will make this true. Well, this will be true if that's true, and this will be true if this is true. So somehow I'm just going to say something like, you know, need this to be true. Need this to be true. So I need it to be the case that the gap between f and l is less than epsilon over b. If I can somehow make the gap between f and l less than epsilon over b, then that will show that the gap between my bf of x function and bl is less than epsilon. Right, well, of course I can make the gap between f and l less than epsilon over b. I can make the gap between f and l less than anything I want. That is built into this knowledge that I have in the red box. The red box says, in some kind of intuitive level, that what I mean when I say that the limit is L, of f is L, is that like I can make the gap between f and L less than any number you choose, right? For any possible epsilon, I can get close enough to see such that the difference between f and l is less than whatever challenge that is. And so now the idea is that there's a lot of sort of variables floating around here, which is one of the things that makes this kind of hard. This epsilon is the epsilon that I'm going to get sort of challenged with in my proof of the statement in the purple box. But what I want to do is turn around after receiving that epsilon and divide that number by b and make f be that close to L. Alright, what am I talking about? Well, I think it's best to just now sort of start the proof. So okay, so here comes the actual proof, sort of beginning now. The rest has just been kind of been set up. Alright, well I plan to prove this statement right here that I need to prove. How does this proof go? Well, I receive an epsilon, or rather I'm challenged with an epsilon, and I need to have a response. So okay, so take epsilon greater than 0. So take an arbitrary epsilon. Alright, now somehow I need to respond with a delta, such that, you know, blah 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 blah. But before I do any of that, I reach into my pocket for the fact that I already know. And the fact that I already know is that this limit is L. And so, since, what's the best way to sort of write this? Okay, I mean, this is kind of a little bit informal, but what I'm now going to do, if we think of these epsilons as challenges, that's how I think of it. So, so challenge, you know, I'll just kind of put it in brackets, you know, the limit as x approaches c of f of x is L. That's a fact. That we're assuming, and by challenge it, what I mean by that is, well, challenge this with epsilon over b. What I mean by this is, if this limit is L, that's my assumption, then for any possible epsilon, blah, 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 blah. Well, the epsilon that the challenge that I choose to sort of feed this is actually epsilon over b. In other words, take the, this is so easy for some people, but it's very hard to explain, maybe, if I want to be perfectly clear, because there's a lot of kind of things going on in the background logic with the way we treat variables. But basically, I'm challenged with an epsilon here, and what I'm going to do with that number, the very first thing I'm going to do with that number is divide it by b. This becomes now a new tiny number, and if b is so 10 or something like that, then I'm dividing epsilon by 10, so it's getting even smaller. And now I'm reaching for the fact that I already know, which is that I can make the gap between f and L as small as I want. Well, I choose to make it smaller than epsilon over b. So, in other words, maybe I'll just write it out like this. There exists a delta greater than 0. No, this is kind of too confusing and too annoying. Let's just say that what happens when I do this challenge, well, I receive a response, right? And sort of like my response is going to be some kind of delta. Let's call it delta 1 or something like that. Response delta 1. What's delta 1? Delta 1 is the delta that I get back from challenging this limit with epsilon over b. After all, in more casual terms, what's going on right here in this line? This line says, yo, give me any challenge whatsoever, and I'll tell you how close you need to get to C such that that challenge is met. Well, my challenge is epsilon over b. How close to epsilon over b do I need, how close to C must I get for my function f to be within epsilon over b of L? Answer, delta 1. And so, what I know is that for all x, if I am pretty close to C, specifically delta 1 is how close I need to get, then the difference between f of x and L will be less than epsilon over b. Alright, so what am I being told now? I'm being told that, delta 1 is how close I need to get in order for this to be true. But my discovery phase said that this is exactly the thing that I need to be true. And so now I am ready to give my answer. I'm ready to give my response. Here's my response. Set delta to just be delta 1. Okay, that's really it. In other words, responding to this challenge now, I respond with delta 1. And what I mean by that is how close you need to get in order to ensure that this is true is exactly how close you need to get to C in this limit to show that the gap is less than epsilon over b. Okay, and now what do I have to prove? I have to prove this conditional. So all I need to do now is sort of show that if I am within C of this delta 1, then the gap between me and BL is less than epsilon. Okay, how can I show this? Well, I just begin the proof, right? So assume that I am within C of delta 1. But if I'm within C of delta 1, then this conditional tells me that the difference between F and L is less than epsilon over B. And, well, now I just multiply both sides by B. distribute the B through. And in fact, I am just done. This completes the proof. In other words, I have just established this conditional. Okay, there's sort of so much going on here and also just so little going on here. I went very, very slowly to try to be thorough, but did it work? Who knows? Perhaps a picture would have been nice. But anyway, there it is. Okay, pause, be right back.